Hey guys! Alright, so today again I'm back to teach you physics. We're gonna do a problem from 2001 today, okay? Alright, so I'll read it to you and then I'll show you the picture and then we'll get started. A ball of mass m is attached to a string of length r and negligible mass. The ball moves clockwise in a vertical circle as shown above. When the ball is at point P, the string is horizontal. Point Q is at the bottom of the circle and point Z is at the top of the circle. Air resistance is negligible, and express all algebraic answers in terms of the given quantities and fundamental constants. So there you go. Okay, so that is the vertical circle that the ball is moving in, okay? Alright, so we're going to get started. A says, on the figures below, draw and label all the forces exerted on the ball when it is at points P and Q respectively. Alright, so I drew that out. Find my circle. That one's kind of square-like, but I think this one's decent. But anyway, at point P and at point Q, they want to know what forces are being exerted on the ball at this time. Okay, so in both points, the ball is going to experience tension from the string and weight. Okay? So weight is always going to be pointing perpendicular down. So on both diagrams, there's weight. mg is equal to weight, right? Okay, but tension is always going to be pointing inwards towards the center of the circle. So at point P, tension is going to be pointing in a 90-degree angle from the weight, but at point Q, tension is pointing directly upwards. See? There and there. Alright, so that's part A. Part B is asking, derive an expression for the velocity minimum, which is the minimum speed the ball can have at point Z without leaving the circular path. Alright, remember again that point Z is the highest most point on the circular path. Alright, so at this point, we're going to do the sum of the forces. So the sum of the forces is going to be equal to the mass times acceleration. Alright? But this is going to be equal to the centripetal force, which is keeping the ball in its circular path. But the centripetal force is always equal to mv squared over r. Hooray! Okay. So now, since the mass is going to be constant on both sides, we are enabled to cross that out. And we know that acceleration is going to be due to gravity. So we have g is going to be equal to v squared over r. Alright, so now we just want to solve for v, and with a little bit of algebra, we get v is going to be equal to the square root of gr, and, well, hold on, v min. Always make sure to label correctly, okay? Alright, so the velocity minimum is going to be equal to the square root of gr. Alright, so now, part C. The maximum tension the string can have without breaking is T max. Derive an expression for V max, the maximum speed the ball can have at point Q without breaking the string. Now, point Q is the bottommost point, alright? Alright, so again, let's step to the sum of the forces. Sum of forces, which is, equal to ma, which is again equal to the centripetal force, right? Okay, but this time, there you go. This time the centripetal force is going to be equal to the tension minus the weight. So you have T minus mg. But again, this is all equal to mv squared over r. Now, what we do is, now again, we're just going to be solving for v squared. So when you isolate t minus mg is equal to mv squared over r. Okay? So basically that's what we have. And again, using a little bit of algebra, we solve for v max this time. So we get v max is going to be equal to the square root of r times t minus mg, which is the weight, divided by the M. Okay? Alright, so that's the V maximum that they're looking for. Alright, so now part D says, suppose that the string breaks at the instant the ball is at point P. Describe the motion of the ball immediately after the string breaks. Alright, so you have to remember that point P is here. When a ball is moving in a circle and the string breaks, the ball is always going to move tangential to the circle itself. So, basically, the ball is going to be moving. See, it's going in this direction, and it's going to go straight up now because it's going to be tangent to the circle, right? I'll draw it for you. Okay, I'm trying to make the circle semi-decent, but it's bigger. Point P and tangent to the curve. Okay? Alright, so this is the circular path. Here's point P, and when it is going this way, it's going to be tangent to the curve, and that is the motion of the ball. Okay? Alright, so we're done with this free response, and I hope you guys were entertained or informed, or either will suffice. Anyways, thanks for watching, and have a great night. Bye!